Okay, I guess it's time to get the show on the road. The current events is something I look forward to very much each year, and I think we have a really outstanding group of speakers this year, so it should be especially interesting and pleasant to listen to. This is motivated years ago by the Bourbaki seminar in Paris, except that when I went to Bourbaki seminars to hear the latest, I often didn't quite understand what was being said, and it wasn't the French. So the goal was to have an A speaks about B's work kind of event, where in fact the lectures would be more accessible and worth listening to if you're not in the field. Anyhow, our first speaker is going to talk about thresholds, sharp and otherwise, a very important phenomena in probability and across many applications of mathematics. He was an NSF postdoc at Georgia Tech and is now back there as faculty member, if I understand right. He got his PhD in mathematics under Joel Spencer at NYU and was then at Yale, or was, sorry, previously at Yale as an undergraduate. And I'm looking forward very much to his talk. Will Perkins.
Yeah, I think so. The clicker, this is the clicker. Okay, thank you very much for the introduction, and thanks for the honor of speaking here. It's really a nice event, and I'm excited to talk about a subject that I find very exciting and interesting. Just so you're not surprised, halfway through the talk, I've been told it's traditional to take a little break, so there's a chance to escape halfway through if you don't like the topic as much as me, but that's fine. So the topic today is random structures and thresholds, and the sort of occasion of this talk is on the recent proof of something called the Kahn-Kalai conjecture by Jin-Young Park, who's actually in the audience, and Park-Pham. And I'll tell you about this and explain why it's important and how it came about. I'm also going to mention another recent, really fantastic result by Deng, Sly, and Sun, proving something called the satisfiability conjecture for large K a couple years before, and show sort of how these fit into the same framework and give you an idea of why both results are very exciting and how they might relate to different fields. So here's the big picture. So random structures of the type that I'll talk about are very easy to define, very simple models, but it can possibly exhibit very complex behavior. And they're important in many different fields, and different fields have their particular questions that they ask about these objects. And this has driven research for maybe 20, 30 years in different fields. And one really nice thing, and we'll see in a couple examples of this, is that these particular challenges have led to the development of very general tools that are applicable beyond the original motivation and outside the original fields where they came from. And hopefully by the end of the talk, you'll agree with me that there's a really beautiful interplay going on between probability, combinatorics, algorithms, statistical physics altogether. Good, so the outline, I'm gonna state the basic model. It's simple to state. I think in a talk like this, it's great to give lots of examples, so there'll be examples throughout the talk. And then I'll really define the main topic of the talk, thresholds, sharp thresholds, and scaling windows. And then I'll explain the significance of these two current events, the Kahn-Kalai conjecture proof and the satisfiability conjecture. And its connection with statistical physics. So that's the plan. I think maybe the most I can hope for from giving a talk like this is that you come away from the talk and want to read something else. There is a survey that goes along with this talk that I just posted on arXiv, so please do read it and give me any comments you have. There are other surveys on the topic of thresholds and random structures that are really, really good. And I've tried to make my survey sort of perpendicular to these, but I wanted to mention them. This survey of Friedgut is sort of, my title is an echo of this talk. Hunting for Sharp Thresholds is his title. The Kalai and Safra paper survey is fantastic and talks about tools that I won't mention at all, but are very beautiful and powerful. Somehow one of the germs of the recent progress was in something called the sunflower conjecture, progress on this, and Rao has a nice survey, actually 2 years ago in this event, and Jin-Young Park has a nice paper on background of the Kahn-Kalai conjecture that she just wrote. Finally, I'll mention at the very end some statistical physics stuff, and if you're interested in more, there's a great textbook by Mazard and Montanari. Good. So what's the object that we're talking about? It's quite simple. It's just the p-biased product probability measure on the discrete cube, 0, 1 to the n. And so what I mean by that is we just go coordinate by coordinate and set the value to 1 with probability p and 0 with probability 1 minus p independently. So the nice example to think about to start is just flipping a coin, whose probability of heads is p, flip it n times. And it seems like this is too simple a structure to have interesting behavior. But what we're going to do is we're going to equip the coordinates, the n coordinates, with different structure. So when you flip a coin n times, you have the order in which you do them, 1, 2, up to n. But we might put different relations on the coordinates that actually give a lot of richness and possibilities to this simple model. Okay, so the questions we'll ask will all be about properties. A property is just a subset of this discrete cube, so it's an event in this probability space. If I say a non-trivial property, I just mean it's not the empty set, not the full probability space. A couple of perspectives that sometimes are useful when you're talking about properties is you can view the property as a Boolean function. So just think of the indicator function of the subset f. This is a function from the hypercube to 0, 1. So that's equivalent, of course. You can also think of a vector of length n of zeros and ones as a subset, with the subset marked by the coordinates that are ones. And so a property also can be viewed as a collection of subsets of 1 up to n. And this will be important later on. Good. The particular properties we'll study will be monotone properties. So monotone, I mean, if you switch a 0 to a 1, the property holds, the property still holds. So here are some non-trivial monotone properties for coin flipping. You flip at least n over 3 heads. You flip a head on flips 11 and on 23. You have somewhere in your flips a run of at least 10 heads in a row. Of course, if you have another head, change the tail to a head, all these still hold. Not monotone properties are, say, flipping an odd number of heads or flipping exactly n over 3 heads, because you can turn the property off by switching. Okay, good. So that's the basic setup, very simple setup, and now I'll sort of explain how there can be some really interesting questions and phenomena related. So here's an example that I will not return to later in the talk, but I really think it's important to see something from probability and statistical physics, because the notion of phase transition from statistical physics somehow is the intuition that's guiding a lot of this study. So this is a simple percolation model. You have a grid, a finite grid of n sites, and each site is declared open independently with probability p. And so I've simulated something with p as a half here, open is, say, red. And one of the questions you can ask in percolation is there an open path of contiguous open sites from the left edge to the right edge? And then you ask about this as the size of your grid gets larger and larger and as p changes. So that's a good example to keep in mind, but it won't be central to this talk. Central to this talk will be random graphs. And so here the random graph GNP is the graph on n vertices in which we include each edge independently with probability p. So here the number of coordinates is n choose 2. And I've simulated on Mathematica 2 different instances of this random graph with different choices of p. And the paper here by Erdős in 1960 that really started the study of random graphs, they call On the Evolution of Random Graphs. And the idea here is as the edge density increases, certain properties, monotone properties, begin to hold, or they emerge. So at some point, triangles will emerge in your random graph, or a large connected component will emerge, or your graph will become not 3-colorable. maybe you'll have a perfect matching in your graph. And this, this paper really showed that as a very simple object of random graph, it still is incredibly beautiful and has lots of complex behavior. But since then, random graphs have been used in many applications as well, both in mathematics as a source of examples and counterexamples, in computer science as a source of potentially hard instances of computational problems. And so this is really a very, very important model in different fields. If you squint and read very quickly the 1960 paper, you'll notice that the model I described is not the model I defined at the beginning. They're talking about a uniformly random graph with n vertices and m edges. But there's a really nice coupling of G and P for different values of P that will recover their model. So what I want to do is I want to generate G and P for all the different values of P at once. And so I'm going to pick uniform between 0 and 1 random variables for each edge. And G and P will be the graph on n vertices where I include all the edges whose random variable is at most P. And so as P increases, I just add edges. So they're coupled in such a way that they're subgraphs of each other. And as P increases continuously from 0 to 1, we add one edge at a time. And this we can call the random graph process, if we look at how the edges are added one at a time and how the graph evolves. And so this is really the perspective of Erdős and Rényi here. So a quick warm-up, let's talk about a simple property, the property of having triangles. So I'll call that FK3. Does G and P contain a triangle? We can approach this with, say, the method of moments. So if X is the number of triangles in G and P, well, let's calculate its expectation. There's n choose 3 possible triangles. You have to have all 3 edges and they're independent, so n choose 3 times P cubed. If we set P to be C over n, then this expectation is asymptotic to C cubed over 6, some constant. And actually, Erdős and Rényi showed you can compute higher moments, and this converges as n gets large to a Poisson random variable with this mean. And then, what's the probability of Poisson is 0? It's e to the minus mean, and so we can really plot the probability that G and P contains a triangle. And it goes from 0 to 1, and this is sort of the type of behavior we're interested in analyzing. But keep this in mind as a simple example. Okay, the last example I want to talk about, and also will be important to this talk, comes from algorithms and complexity. And here, the random model we're talking about is a random instance of a computational problem. And so, what's the original NP hard or NP complete problem? It's Boolean satisfiability. And so FKNP, random KSAT, will be a random instance of Boolean satisfiability. It will be a formula on n Boolean variables, and each possible K clause will be included independently with probability P. So here there's a variable and its negation, so 2n literals, 2n choose K are the number of possible K clauses. So here's a 3-sat formula. The V's mean or, and the upside down V's mean and. So this says x1 or not x3 or x7, and not x1 or not x2 or not x4, and so on. And so this is a Boolean satisfiability formula. And the question is there an assignment of true and false to the variables so the whole formula evaluates to true? And so this one's easy. You can set x1 to be true, x2 to be false, x5 to be true, and you satisfy the formula. So this formula is satisfiable, but you can form the random KSAT or random 3-sat formula and ask, as a function of K and P, is this random formula typically satisfiable or not? And also a very nice question is, if it is satisfiable, can you find a satisfying assignment? So there's an algorithmic question here. Another picture of a paper here. So this is a paper from 1992. And if you squint closely, you'll see that people were studying artificial intelligence way back in 1992. So it's not a brand new thing today. And these researchers, Mitchell, Selman, and Levague, they were using SAT solvers in their AI models. And they really wanted to know, SAT is NP hard, but does that really matter? And people had been studying, say, uniform distributions on satisfiability formulas and observing that these were always easy to solve. But the three of them said, refined the probability distribution and say, okay, let's fix the clause length. Let's fix the clause length to k, or to 3 in this case. And let's vary the clause density and try different distributions on these random formulas. And the plot here is an empirical plot of, they generated these random formulas with, the different curves are different numbers of variables, increasing numbers of variables. And they ran some heuristic algorithm and saw how long it took to solve the instance. And they observed a spike in the computation time. And they also observed that this spike, basically the density of clauses to variables was about 4.2, 4.3. They also observed that this is right around the point at which the formulas went from typically satisfiable to typically unsatisfiable. And this excited a lot of people in both computer science, mathematics, physics. This looks like some sort of phase transition phenomenon. And it's saying we have a way to generate, in a very natural way, hard instances of this classic problem. And so it's sort of hard to overstate how exciting this was and how many people got involved and started working on this after these observations in the early 90s. So just to connect those two models, another equivalent viewpoint is you can view random k-sat as a random hypergraph. And so here we have two n vertices, one for each literal, a variable, and its negation. And you can, what are we doing? We're picking a collection of subsets of size k. And a subset of k vertices, that's called a hyperedge. And so we have here a random 3-uniform hypergraph. And we can define, similar to GNP, we can define GKNP as a random k-uniform hypergraph in which each edge is included independently with probability p. And this will be important in what's to come. Good. So those are somehow the key examples here. What are the basic questions we can ask about monotone properties in general? We said we have non-trivial monotone property. The probability that this property holds starts at 0, ends at 1, and it's a continuous, strictly increasing function. So it's something like this, the plot. And really the question is, how does it increase from 0 to 1? We know it has to increase from 0 to 1, but how does it do it? In particular, what's the right way to scale the x-axis so we see this non-trivial behavior? And we can define the critical probability just to be the p, so that the probability this property holds is exactly 1/2. This exists because it's a continuous, strictly increasing function. So that's PC, the critical probability. I'll remark, and I've sort of implied this, but we're almost always interested in not actually just one property, but a sequence of models as some parameter n goes to infinity, and a sequence of monotone properties. So implicitly, there will always be this underlying parameter n, maybe the number of vertices in the graph, the number of Boolean variables, the size of the two-dimensional grid and percolation. And we'll use asymptotic notation, the usual big O, little o notation. And we'll also say that an event or a sequence of events holds with high probability if the limit of the probability of these events is 1. But this will always be our perspective, the asymptotic perspective. Okay, so what are the tasks? Task number 1, we would like to understand where is this critical probability. Either find, say, first order asymptotics of the critical probability, or at least the asymptotic order up to constants. And so this is task number 1. And Erdős and Rényi, way back in 1960, in this first paper, made a very nice definition of a threshold function for a monotone property. And PT of n, it depends on n, is a threshold function for this monotone property. If when p is much larger than pt, the probability tends to 1. And if p is much smaller than pt, the probability tends to 0. And so then, note that this threshold function is not unique. It's just defined up to constants. So if pt is a threshold, then 10 times pt is also a threshold. We saw for triangles, the threshold was 1 over n, or 2 over n, any constant over n. And we'll say colloquially that a property f emerges at its threshold. Okay, so 20 years later, 25 years later, Bolabash and Thomason actually showed that this is really a good definition in the sense that every non-trivial monotone property has a threshold function. And in particular, you might as well take PC to be the threshold function. So the thresholds always exist. You know, I hear sometimes every talk should have a proof. So here's the proof. It's 2 lines. This is not the original proof, but this is sort of a modern coupling proof. So imagine P, you choose P so that the probability your property holds is epsilon. And then you multiply P by a big integer K. Now the claim is that now the probability the property holds is at least 1 minus epsilon to the K. Why is this? You just take K independent copies of your random structure and take the union. By monotonicity, if any of the structures has the property, then the union has the property. And so the probability you don't have the property is 1 minus epsilon to the K. And then you just take K to be log 1 over epsilon, and now the probability has gone up to 1 minus epsilon just by multiplying by a constant factor. So that's the one proof you'll see in the talk today. In the same paper, Erdős and Renyi went further and characterized a special type of threshold. And so they said a property F has a sharp threshold if for every small constant epsilon, when P is at least 1 plus epsilon times the critical probability, the probability tends to 1. And when P is at most 1 minus epsilon times the critical probability, the probability of the property tends to 0. So a much sharper transition from 0 to 1 than just what's guaranteed by a threshold. And then we say if a threshold is not sharp, it's coarse. And so in particular, the property of having a triangle we saw is a coarse threshold. For any C, and P is C over N, there was the probability of having a triangle is somewhere between 0 and 1. Okay, so this is task 2, and task 2 is, given a monotone property, does it have a sharp threshold or does it have a coarse threshold? And this one, actually, we have a very satisfying answer. So here's our first example of a very general theorem motivated by a specific problem, but now applies to the entire area. So Friedgut actually was motivated by the satisfiability problem, the random k-sat problem. And what he proved is that a monotone graph property is coarse only if it can be approximated by the property of containing one of a list of constant size subgraphs. And then Bourgain wrote an appendix to this paper that generalized this theorem to general monotone properties and not just graph properties. In particular, Friedgut proved that random k-sat has a sharp threshold, and this was the motivation. So essentially what this says is that the only properties that do not have sharp thresholds are ones that are like this simple property of containing a triangle. So that's the only way you can have a coarse threshold. Another way to say it, and this is from the surveys I mentioned, is you should always expect a sharp threshold unless there's a very good reason not to. And because it can be approximated by this subgraph containment. And so task 2, at least, we have a very satisfying, very general answer to this problem. The third task I want to talk about is about scaling windows, and this is a bit more quantitative. So the scaling window, or the width of the scaling window of a monotone property, is the amount you must add to P to raise the probability of your property from epsilon to 1 minus epsilon. Okay, so additive difference between these probabilities. Bolabash-Thomason theorem, what does it say, or the proof that I just gave? It says that the width of the scaling window is big O of the critical probability. It's enough to do a constant times the critical probability to raise the probability. And what is a sharp threshold? The sharp threshold is exactly when the scaling window has width little o of the critical probability. But you can ask for much more quantitative bounds, and so that's task 3. If we're given a monotone property, can we get good bounds? Can we determine the asymptotic order of the scaling window? Of course, if the threshold is coarse, we know what it is, but if it's a sharp threshold, there's many possibilities for the width of the scaling window. So for triangles, as we saw, the width of the scaling window is 1 over n. So maybe I'll take is now the proper time for the quick break? Sure. Okay, so just stretch your legs, introduce yourself to your neighbor if you like, and we'll Okay.
Feel very on your ease, but now everybody is hearing you.
No, yeah.
Don't get too happy. There's lots more good stuff to come. Let's get back to work.
Okay. Welcome back from your break. So I want to talk about some examples of these 3 tasks and different properties and things like that. So the first one is in the random graph, talk about perfect matchings. So here I have a graph, and what is a perfect matching? It's a disjoint set of edges, so they don't touch, and they cover all the vertices. So the red edges in my little picture, this is a perfect matching. Of course, you need an even number of vertices to have a perfect matching, but you can ask, what is the threshold for GNP to contain a perfect matching? Okay, this is a nice question. There's an easy lower bound, and the lower bound comes from saying that if you have a vertex that's isolated, that is not touching any edges, then definitely you can't have a perfect matching. Okay, easy enough. And using method of moments, it's very easy to understand the property of having an isolated vertex. Okay, harder, but not super hard, and this was proved by Erdős and Rainey, is that the lower bound is tight. Log n over n is a threshold for perfect matchings. Okay, so this easy lower bound actually determines the right threshold. Actually, much more is known, so there's a hitting time result. So look back to the random graph process where we're coupling these random graphs, adding one edge at a time. And a hitting time result says that the very moment, with high probability, the very moment that we lose the last isolated vertex, so take the last vertex of degree 0 and add an edge to it, actually a perfect matching with high probability will exist right then. And so actually then we really know a lot about the property of perfect matchings because we can just read it off from the property of not having an isolated vertex. And so we can find the scaling window is order 1 over n. So this is a sharp threshold. Remember the threshold is log n over n, scaling window with 1 over n. So that's great. So we really understand perfect matchings very well, just as well as we understand like having triangles. Let's make it a little bit harder. So now I have a random hypergraph. So this is a picture of a 3-uniform hypergraph. And the perfect matching in a hypergraph is just the same. It's a set of disjoint edges that cover all the vertices. So this is a perfect matching in this 3-uniform hypergraph. And then you can ask, what is the threshold for perfect matchings in a random hypergraph? Well, there's an easy lower bound, right? If you have an isolated vertex, again, you can't have a perfect matching. And so the lower bound is log n over n to the k minus 1. Now it's much, much harder to prove the upper bound. And so this was a problem that was open for 30 years. So Shamir posed this problem in the 70s. It became known as Shamir's problem. And it sort of drove a lot of research in probabilistic combinatorics and random graphs. And finally, in 2008, in a difficult proof, Johansen, Kahn, and Vu proved that, in fact, this is the answer, that log n over n to the k minus 1 is the threshold. But it was a challenge, and it took a long, long time. It was not like perfect matchings in a graph. I will say that very, very recently, actually, even the hitting time result is now known. So in a fantastic paper of Jeff Kahn, he proved the hitting time result. As soon as there's no isolated vertex in the random hypergraph, then there's a perfect matching. And so now, finally, we really know everything about this problem. But this was hard work. Another graph property, there's actually just one open problem left from the original 1960 Erdos-Renyi paper, and that's the following. When does the random graph become not Q-colorable? And so, or find the asymptotics of the critical probability for the property of being 3-colorable, let's say, or not 3-colorable if you want it to be monotone. It's very easy to see using like first moment method or other arguments that the critical probability is on the order 1 over n, but we really now, the question is, what's the asymptotics of the critical probability? Using Friedgut's theorem, Aklioptas and Friedgut showed the threshold is sharp, so we know it's sharp. And the conjecture is that there exists some constant that depends on the number of colors, so a constant c for each q, so that the critical probability of this q colorability is asymptotic to cq over n. And actually, not only do we not know what this CQ is, but we don't even know that this CQ exists. And that's still an open problem, the one open problem from the paper. And hopefully by the end, you'll sort of see why this is still open. It turns out the predicted answer comes from a completely different discipline, and sort of you never would have predicted the answer from combinatorial considerations. Very much related, now I can define the satisfiability conjecture. Satisfiability conjecture is for each k at least 2, there's some alpha k, so that the critical probability for random k-sat is asymptotic to alpha k over n to the k minus 1. And this was posed very soon after this early 90s paper with the empirical observation. And it was quickly proved for k equals 2. So k equals 2 is special. 2-sat is not NP hard. It's not a hard problem. And so actually satisfiability or unsatisfiability in random 2-sat is like having a giant strongly connected component in a random directed graph. So this is a special case. But for larger k, it was open. And Friedgut sort of almost proved this. He established sharpness, but actually his result leaves open the possibility that this alpha k actually varies with n. And so the satisfiability conjecture really is that there's a constant alpha k, so that we have this asymptotic formula. Okay, good. So those are some motivating problems. And now I'll get to the sort of heart of the talk, explain this current exciting progress, the current events, why we're here. So, Kahn and Kalai in 2007, motivated by Shamir's problem, this very challenging, difficult problem with a very easy lower bound, made a sort of bold conjecture. And basically what they were asking was, could it be true that the best easy lower bound on PC is actually not too far from the truth? Okay, so I need to tell you what I mean by best easy lower bound. and we'll have some definitions. So again, F will always be our monotone property we're interested in, and then we'll have some other objects. So we'll say a property F is P small if there's a cover G. So this is another subset of the discrete cube, so that the following two conditions hold. The covering property is that for each set, now I'm going to use the subset, family of subsets language to describe a property. For each set in F, there is some S in G, so that S is contained in T. And then we want, if we sum over all the elements of S, P to the size of S, we want this to be at most 1/2. I think if you haven't seen this definition before, it's a little hard to parse with these formulas, but this is a good example to keep in mind. Imagine we have properties FH and FH prime, and these are properties of containing some subgraph H or H prime. And if H prime is a subgraph of H, then FH prime is a cover of FH, so it satisfies the first condition here. Okay, so you can imagine, if you have some complicated subgraph and there's some piece of the subgraph that's unlikely to appear, you could do a first moment argument on that piece of the subgraph. And this notion of being P small captures this type of argument. And so the expectation threshold of F is just the largest P for which F is P small. Okay? And the nice thing is that this gives a lower bound on the critical probability. So in this sense, it's the best possible easy lower bound. Although there's many, the set G is a subset of the discrete cube, so there's many possible candidates for best possible easy lower bound, so it's not necessarily easy to find the best. But this is a lower bound. And the question is this best possible easy lower bound close at all to the truth? Okay, and this is what Kahn and Kalai conjectured. They conjectured the truth can't be too much larger than this lower bound, and Jin-Young Park and Park-Pham prove this, and this is the proof of the Kahn-Kalai conjecture. So formally it says there's an absolute constant K, so that the critical probability of any monotone property is bounded between this expectation threshold and K times the expectation threshold times log L of F. And L of F is the maximum size of a minimal element of F. So in particular, like if it's at most n, so you can take log n here, but if your property was like containing a triangle, then the maximal size of a minimal element is just 3. So it could, this could even determine your threshold up to constants. And this is the theorem. And then we'll see in the minutes to come, we'll see how this is very, very useful. So to see why it's useful, I want to reformulate this using optimization language. And here, I'm writing an integer optimization program here. The variables are g of x. So g of x takes values in 0 and 1 for every element of the hypercube. So think of this as the indicator function of your potential cover G. Okay? The bottom equation, or the bottom constraint, is this condition number 1 in the definition of a cover. You have to cover it. And then you're minimizing the sum over all the elements of P to the size. Okay? And so in particular, if you can show that V of Fp is at least 1/2, then we know that Q of F is at most P, and by the Park-Pham theorem, the critical probability is at most Kp log L. Okay, so that's an optimization version. Why do I want to do this? Because I want to do linear programming relaxation. Integer programming is very hard. Linear programming is not so hard. So we can relax this optimization problem. And so the only change I've made is now I allow G of X to be a value between 0 and 1, instead of having to take integer values 0 or 1. And with this relaxed optimization problem, we can define the fractional expectation threshold. QF of F, it's the largest P for which VF is at most 1/2. Okay, so this is just think of this as some relaxation of the notion of the expectation threshold, a fractional version. And again, and this is in the survey, but it's very easy to see that the fractional expectation threshold gives a lower bound for the critical probability. And actually, a result of a couple of years ago by Frankston, Kahn, Narayanan, and Park, they proved what's called the fractional Kahn-Kalai conjecture. This is a weakening of the Kahn-Kalai conjecture by Talleyrand, and that's that the fractional, the critical probability is not too much more than the fractional expectation threshold. So this was conjecture by Talleyrand. It's weaker than the Park-Pham theorem, but as we'll see, it actually, for the known applications, this theorem suffices. Okay, so how do we use this? Now I'm in a computer science department, and so, let me say that this proof built heavily on this really nice work of Always, Lovett, Wu, and Zhang on the sunflower conjecture. And so this is written about in Rao's survey that I mentioned. Okay, and so if you have a linear program and you want to understand it, one thing you'll often do is look at the dual. And so we can take this fractional optimization problem and look at the dual. And so what the original optimization problem, we had a variable for every element of every possible subset of n elements, and we had a constraint for every element of f. Okay, so in the dual, we're going to have a variable for every element of f and a constraint for every subset of 1 up to n. Okay, and if you construct the dual, now it becomes a maximization problem over the variables are these nu of t, where t is are your sets in f, and it has to be non-negative, and you want the sum over all the sets that contain a particular set S to be bounded by p to the size of s for all s subsets of the cube. Okay, so this is, you can just write this down. But what's nice is that there's a really nice interpretation of this dual program in terms of probability distributions. And so this is due to Talleyrand. And the right definition is a probability measure nu supported on F. This is your monotone family, your monotone property, is P spread if for every subset of the Hamming cube, the probability that you're contained in a random element drawn from nu is at most twice p to the size of s. Okay, and so this is the definition, but what it says is the measure is spread if it's not too likely to get some clump of elements in this random measure. And in particular, it's roughly like it should be if your elements were chosen independently with probability p. So this is a p spread measure. And the implication of duality and the fractional Kahn-Kalai now theorem is that if your monotone property supports a p spread probability measure, then we have an upper bound on the critical probability. The critical probability is at most constant times p times log L. And okay, so I wanted to go through the details of that, but the takeaway message is very simple. Now the search for thresholds, due to these recent breakthroughs, is the search for a spread probability measures on your family. Okay, and so it's a completely new technique for locating thresholds, and we'll see it's extremely powerful. So for one, it gives a very easy proof of the Johansen-Kahn-Vu result. And how do you do it? Remember, the threshold was log n over n to the k minus 1. So it will be enough if we can show that some distribution, and why not take the uniform distribution, is order n, 1 over n to the k minus 1 spread. Okay, I'll give you one exercise to do after the talk. Here's the exercise. So you want to know, what do you have? You're going to find some probability measure on perfect matchings of a hypergraph. And what you want to show is that there's no set of hyperedges that's too likely to appear as a subset of these edges. Okay, so our distribution is actually just going to be on perfect matchings. And so for a subset of edges to appear, it has to be a matching itself. And so you can fix a matching of size t. They all look the same by symmetry. And now you want to compute the probability that these t edges are in a uniformly random perfect matching. Well, this is just the number of perfect matchings on the remaining set of vertices, which you can compute, divided by the total number of perfect matchings on all the vertices. And this is like a telescoping product. You can compute it, but what you can see is that this, you have a nice upper bound, some constant over n to the k minus 1 raised to the tth power. And so this measure is order 1 over n to the k minus 1 spread. And this immediately implies via the duality and the theorem that the threshold is on the order log n over n to the k minus 1. It's fantastic. It's a general purpose theorem and proves this result that took many, many decades to solve. Caveat, it does not imply the more recent results of Jeff Kahn on the hitting time. So it doesn't solve all your problems for you, but it's very powerful. Good. So that's a result where we had a difficult proof and now we have a simple proof. What's maybe even more exciting is problems where we had no idea of what to do, now we have a proof. And so this is a really nice combinatorial example. A Latin square, maybe if you do Sudoku puzzles in the airport, you know what a Latin square is. A Latin square is an n by n array, and in each row and each column, you have to list the numbers 1 to n, but so that every row and every column has exactly one up to n. So I've drawn a Latin square of order 8. And you can ask lots of questions about Latin squares. How many Latin squares are there of n, and things like this. But we want to turn it into a random problem. And so Johansson had the idea of the following model. For each cell in our array, we're going to pick a random list of integers by including each of the n possible integers with probability p. And now, independently over the different entries. And now we want to know, is there a Latin square that respects the entries? So you can only use the integers in your list, and we still want a full Latin square. And what's the threshold in P for the existence? Again, there's a very easy lower bound. If you have an empty list somewhere, there's no way you can have a Latin square. Or if you have a row that misses an entry or a column that misses one of the numbers 1 up to n, there's no way to have a Latin square. And that gives you log n over n as a lower bound. But really, before the recent results, there was no good upper bound at all. And now with these results, the task becomes find a well-spread distribution on Latin squares, which is quite an interesting problem and really novel. It's not at all like anything that came before. And actually, it's not known how to show that the uniform distribution is well-spread. This is an open question. Tom Kelly at this meeting, a nice talk related to this. But instead, what you can do, you don't have to show the uniform measure is well spread. You can construct any probability measure that's well spread. And so what has been done is that some other advanced techniques from probabilistic combinatorics, random greedy processes, iterative absorption, something called the LLL distribution, have been used to construct other distributions, not uniform, but showing that they're spread. And so there's a series of 3 papers that came out in the last, say, 2 years. Saw, Sani, and Simpkin proved the first real non-trivial bound on this critical probability. They proved it's n to the minus 1 plus little o1 in the exponent. Then Kang, Kelly, Kuhn, and Methuku proved that the critical probability is order log squared over n. And so a log factor off the lower bound. In particular, how did they prove this? They found a distribution on Latin squares that's order log n over n spread, and then you lose the extra factor log n from the theorem. And then independently, last year, Kibosh and Jain and Pham proved the conjecture. And so at least up to constants, this easy lower bound is tight. And both papers proceed by constructing in very clever ways spread distributions, order 1 over n spread distributions on Latin squares. And so I think this is one of the takeaways from this talk. By first of all, the coming up with the conjecture and then proving the conjecture in the fractional version, we've established a completely new tool that changes the way we look for thresholds. And I expect there'll be many, many more applications coming along. In the last few minutes, I want to talk about random KSAT. and some of the other tasks I mentioned besides task 1. And what does statistical physics have to say about random k-sat? And here's like I'm almost embarrassed to give a one-slide overview of this development, but here it is. So statistical physicists want to study glass, like the glass that's in your house or something. And they came up with something called the Edwards-Anderson model, which is something called the spin glass on the d-dimensional integer lattice. It's like an Ising model, but the coupling constants are random variables, they're Gaussians. It turns out this is really, really hard to analyze. It's too hard. And so the Sherrington-Kirkpatrick model is taking the same model, but the underlying graph is much simpler. It's a complete graph. Every vertex interacts with every other vertex. Okay, this is easier to analyze, and it has some very beautiful behavior. Parisi actually proposed a solution, and then this was proved. And so this model is considered solved. And then you can try to go somewhere halfway between a lattice and a complete graph. And you can recover some geometry by looking at the spin glass model, but on the Erdős-Rényi random graph, say with probability P is like D over N. And these physicists, Parisi, part of the reason Parisi won the Nobel Prize in 2021 was for this work exactly. They developed methods called the replica method and the cavity method for analyzing spin glass models on random graphs. And so they came to these same models that have been studied in computer science and combinatorics for their own very particular reasons of glass. And what is the cavity method? The cavity method, they take a different perspective on thresholds. Instead of asking, is there a satisfying assignment to my k-sat formula or not? Is there a 3 coloring in my random graph or not? What they say is, let's look at the uniform distribution on solutions and study the properties of this distribution, the Gibbs measure in their language. And by making some very strong assumptions about the structure of correlations, okay, this is called the replica symmetry breaking hypothesis, they then do mathematical calculations and come up with predictions. So they're really doing math. It's not like they're simulating these models on big computers and then looking at plots and pointing at things. They're making some very, very strong assumptions and then doing math. And they're quite good at math, it turns out. And they came up with some very precise predictions for, say, the threshold for random k-sat, the threshold for random graph Q coloring, and also the cartoon I have is sort of how the set of solutions evolves as the density changes. But the method is not rigorous. There's no proof of the replica symmetry breaking hypothesis, and so this is non-rigorous. What Ding, Sly, and Sun did in their proof, and this followed a lot of previous work, was to do very advanced versions of the first and second moment methods. And so, you can do the first and second moment method, but you can condition on some events. You can look at different random variables. Instead of doing the first moment method or second moment method on the number of solutions, they actually did it on the number of clusters, which I won't define, but you see in the cartoon. And this is actually exactly what's predicted by the cavity method. It's predicted that this is the right thing to do. And then they were able to implement this. They needed to take k large, so the satisfiability conjecture is still open for, say, k equals 3. And I mean, it's scary to think. The paper is 388 pages in the journal version. And so it's a fantastic achievement. It validates the cavity method prediction. But it's not a general purpose tool, like we've seen in some other cases. And in particular, it seems completely insurmountable to do this for random graph coloring. And so that problem's wide open. And how do they prove the satisfiability threshold conjecture? They do it by identifying the threshold. You could hope that there's a method to prove this conjecture without identifying the threshold in a sort of more generic way, but we don't know that. I'm going to say just one thing about scaling windows. We've seen general methods for locating thresholds, proving sharpness. If a property has a hitting time result, then we can often determine the scaling window. But we really know very little about scaling windows. There's no general theory at the moment. I won't go through this slide, but just to say there's another really nice random model of constraint satisfaction problem motivated by neural networks from the 60s. And Altshuler and then Saw and Sawhney identified the scaling window here. And this is a problem that does not have a hitting time result. It's thought to be hard near the threshold. So there is some really interesting advances on this part. Okay, but that's really what I want to say. The summary, we have some great and some new general purpose tools for understanding thresholds. So we have the old theorem of Freegut, and we have this brand new Park-Pham theorem and the fractional version. But for some of the other tasks, we don't have these tools. So we have the cavity method that gives a general way to predict thresholds. But at the moment, we only have this one standout result verifying it, and we don't have general tools to either understand how to locate the first order asymptotics or to understand scaling windows. And so I'll conclude there. Thank you very much.
Thanks for this terrific talk on this subject, far from my expertise, but wonderful to hear about. There's time for a question or two, well, maybe one question before. If you want to ask a question, find one of the mics. There's one in each direction there. And otherwise, in a moment, we'll go on to the talk by Hussein Murtada. If you're not amazed by his result, your money back. Don't go away. Yes, question there.
So the typical satisfiability problem, right? The famous one is still open, of course. Like whether it's, yeah. Anyway, the point is, what does this result say about that one?
The Park-Pham result?
Yeah.
Nothing, because it just
doesn't.
It identifies thresholds up to constant factors. So it's about problems that are really difficult to locate the threshold. For random k-sat, it's quite easy to say it's order 1 over n to the k minus 1. That's not the difficulty is the constant in front. And so they're really different accuracies of identifying thresholds.
I see. So it doesn't really shed that much light on that problem. Yeah.
No, but I think it gives some hope that general purpose tools can be constructed. We should be looking for these things.
Okay. Yeah, thanks.
I see another question waiting, but maybe you should just walk up and ask Will in person.
Oh, that's fine too. Yeah.